Sunblock was first invented by chemist Franz Gretner in 1938. The first sunblock had a protection factor of 2. Sunscreen benefits society today because without it we would not have any protection from the sun. Nowadays, sunscreen is useful because it is used in everyday life, and now has been incorporated into other skincare products such as moisturizers, makeup, and facial cleansers. The chemistry behind sunblock includes reflective particles that are made up of zinc and oxide and titanium oxide. The zinc oxide provides a white color in the sunblock, even though most of the oxide particles are small. Plants use photosynthesis to convert light energy to chemical energy by storing energy in bonds of sugar. Without oxygen, sunlight, and water, plants would not photosynthesize and then would die. We applied sunscreen on the leaves to block sunlight and stop the photosynthesis to see if the SPF factor is really effective.
The purpose of our lab is to research and experiment on whether the sun protection factor of a sunscreen corresponds to the amount of coverage from the sun they provide.
The independent variable is the SPF level of the sunblock. The dependent variable is the condition of the leaves after 2 days in the sun, which shows the amount of sunlight that got through to the plants, and therefore the strength of each SPF of sunscreen compared to one another. The controlled variables are the amount of sunblock, the brand of sunblock, the amount of water available for each plant, the temperature of the surroundings for all the plants, and the amount of sunlight. Our hypothesis is that if the SPF of the sunscreen applied to the leaf is higher, then less sunlight will get through to the plants, and the leaves will become more wilted. This is because the higher the SPF, the more coverage from the sun's UV rays and energy. The higher the SPF, the less sunlight gets through to the plants, and less of the necessary process that a plant needs to stay alive, photosynthesis, can occur. First, we fill each cup with 1/4 cup of water. Next, we label each of the 4 cups with SPF 15, SPF 30, SPF 50, and controlled.
Next, we cut off 8 leaves from a specific plant.
Here we have all 4 cups labeled control, SPF 15, SPF 30, and SPF 50. All 4 of the cups have 1/4 of distilled water inside them. 8 leaves that we picked from the garden outside. They are all of the same plant. Now, we will put the SPF 15 on 2 of these leaves, SPF 30 on the other 2, and SPF 50 on the other 2. The last 2 leaves will be put in the controlled cup, and they will have no sunscreen on them. After you have applied sunscreen to each of the leaves, 2 with SPF 50, 2 with SPF 30, 2 with SPF 15, and 2 without any sunscreen, you will put them into each cup according to the labeled cup. Now, we'll take the leaves outside into broad daylight where they'll stay for approximately 2 days over the weekend. Here we have all 4 of our trials out in the broad sunlight.
After a 2-day long period, you can tell there's differences between a sunscreen. For example, here in a control, it's still green. Here in SPF 15, it's beginning to turn yellow, but it's still green. Here for SPF 30, it's still you can see the sunscreens in the pores. And here for SPF 50, it's beginning to turn brown and wilt.
When we were first thinking about the way to do our experiment, we set up a procedure that would use a UV monitor to measure the amount of UV rays that were projected onto a clear piece of plastic when it was covered by the 3 different SPF amounts of sunscreen. When we got to class, we realized that the school did not have a UV monitor, and it would be too expensive to go out and buy one. So we changed our procedure, with Miss Cliff's advice to use plants to observe the difference that different SPFs make on blocking sunlight and plants not being able to carry out photosynthesis. We brought our experiment outside. We applied the sunscreen to all of the plants and set up our new experiment outside of Cafe Licio at school. Soon we came to the realization that we would have to leave the plants there for more than 1 class period in order to get results. We could not do this because there was the possibility of the plants flying away, someone walking by and stepping on them, and many other factors we could not watch over and control. Next, we decided to do the same experiment except underneath UV lights in a very dark room with no light pollution. We left the leaves there for a day, but when we came back to observe them the next day, the bulbs had burned out. Needless to say, that experiment did not work. Then we decided to restart our experiment, get new plants and fresh water, and put the plants outside in my backyard over the weekend. This way, I was able to monitor the plants every day, and a direct stream of sunlight was provided, besides the occasional clouds. This experiment was the one that succeeded as being controlled and precise, so we used it to create our project. The procedure was built around a scientific approach to testing our hypothesis, and we incorporated chemistry into it. For example, we made sure we had only one independent variable and one dependent variable, so that the chemistry of the sunscreen and the leaf were not disturbed. We filled each cup that the leaves were placed in with water because the plants need sunlight, oxygen, and water in order to undergo photosynthesis, produce their own food, and stay alive. We made sure the leaves were under direct sunlight and no shadows were cast over them. Also, we waited 2 days to record our observations because we know that it would take that long for a leaf to undergo the chemical process of wilting. We followed the procedure that was written in the pre-lab and little changes were made. However, one change we made was that we did not directly label the cup with the SPF label on it. We labeled the napkin that it was placed on top of.
The data is telling us that sunscreens with lower SPF did not cause the leaves to wilt. This is shown through our test in using SPF 15. After a 2-day period, the leaves did not wilt and remained green and shiny. Higher SPFs, however, tend to cause the leaves to wilt after a 2-day period. This is shown through our test in using the SPF 50. After a 2-day period, the leaves were seen to wilt and turned into a browner color.
This fits what we said in our hypothesis because the leaves with a higher SPF wilted while the leaves with a lower SPF didn't.
The data does fit in the theory of our research because in our research it says that by covering the leaves with SPF sunblock, it would cover the stomata and would not allow the leaves to photosynthesize. If the leaves were unable to photosynthesize, then the leaves would wilt and die. Our data fits with the theory of this research because leaves with higher SPFs had a greater effect after a 2-day-long period in comparison to leaves with lower SPFs. This is because the leaves with higher SPFs had blocked the leaf stomata, causing it to not photosynthesize well enough. The chemistry of our experiment includes the process of photosynthesis and how sunscreen can affect the leaves to wilt or not. Photosynthesis is caused from the sun and is traveled into the fields, including grasses and leaves. If photosynthesis comes into contact with the leaves, then leaves would grow and turn green. Since we used sunblock in our experiment, the sunblock had blocked the leaf stomata, causing the leaves to not come in contact with photosynthesis. Because of this, the leaves would wilt and die. This is shown in our experiment because the leaves that were covered by higher SPF levels had a higher effect than leaves that were covered by lower SPF levels.
An error that could have occurred in this lab is that the sunlight could have been affected, either with clouds or shadows cast on the walls of the house, which might have covered some plants but not others. Another error in this lab is that the leaves were different sizes. Even though only slightly, this could have tampered with the results, and different amount of sunscreen and water would be needed to fulfill the needs of the leaves. Another error in this lab is that the leaves might have been getting different amounts of sunlight because they were set up in different positions. Next time, an improvement would be that all the leaves were exactly the same size and the leaves would be put in a controlled environment. The wind, rain, and different amounts of sunlight available makes it hard to measure the results because there wasn't a set measurement that we used to show how much sunlight or wind or rain that affected the results. Another improvement we could have made in this lab is that it could have been done in a controlled environment or a scientific lab or setting. This way we could have monitored all the variables instead of leaving it to nature. One last improvement that we could have made in this lab was to make sure that all the sunscreen applied equally on all the leaves, and so it would be more regulated. From this experiment, we've learned there is little difference between SPF 15 and 30, however SPF 50 does provide full coverage and lasts for a long time. We know this because SPF 15 sunscreen faded on the leaf, while SPF 30, however, slightly faded, and SPF 50 remained white. This stopped photosynthesis from occurring in the leaf.